Okay, so the final chi-square test that we're going to look at is going to address relationships between two categorical variables. And so to do this, you need things to come from your data has to come from a single random sample. So not from two separate samples, or from two separate groups or anything like that. It needs to come from a single random sample from a single population, and then that sample from that one population is classified based on two categorical variables. So maybe you took a single random sample from the population of people in Mesquite, and then you classified something based on gender and then based on something else, maybe a preference for something. Okay, but you only took one sample, and then you classify that one sample by two different categorical variables. Okay, so let's look at this example here that talks about relationships between two categorical variables. So pause it and take a second and read what's going on with the scenario. Okay, so now that you've read, part A here is talking about is this an observational study or an experiment, and then you need to back that up, whichever one you chose. So for this one, this would be an observational study. Okay, and my justification or my support for that, since it's an observational study, my justification or support for that here is that there was no treatment imposed. Okay, there was no specific treatment. This was just from this particular population, we observed what we found, okay, or what we saw, recorded what happened. Okay, but there was no treatment posed by the person doing the research. So part B here says to make a well-labeled bar graph that compares coronary heart disease rates for the different anger levels, and then describe what you see. So if we're making a bar graph, your bar graph should look something along the lines of this. So we've labeled with units our X and Y axis. Okay, our anger rating here is a bar graph because we just have these low, moderate, high. I can't do a line graph or anything like that with those. You'll notice I only graphed the percent with coronary heart disease. I did not graph both things, the ones that did not get coronary heart disease. First of all, because I can just subtract from 100 to figure out if I have the percent with coronary heart disease, I can figure out the percent of people that did not have it. And second of all, because it would really just be too tall. You know, for a lot of those, these percents are in the 80s, the 90s, and so we'd have really, really tall bars, and it would be difficult to be able to compare the ones that actually had coronary heart disease. Okay, and so our next step from here would be to determine whether the data shows an association, or could the association that we might see, like based off this bar graph, we look at this and we think, you know, it kind of jumps out that the higher level of anger, the higher the risk of coronary heart disease. But what we're looking for, is there truly an association between those two things? Or could that association have come from poor sampling, from a lack of sampling, and that it's not really true? So we'd go ahead and we perform our significance test. And this is where our chi-square test will come into play. So with any significance test, one of the first things we need to do is we need to determine our hypotheses. So for these, our null hypothesis is that there is either no association between the variables, and remember this would all need to be in context. For example, for our last one, you would say that there was no association between a level of anger and coronary heart disease. Or you could also word that as that the two variables are independent. And if you think back to independence, that means the likelihood of one does not change the other. So hold on, so the two variables are independent. And think back, remember our probability of event A given event B. And if they're independent, it doesn't matter that if event B occurred, it's still the same probability as if it had not occurred. That would make them independent. So our null hypothesis is either that there's no association between our two variables, or the two variables are independent, which means that our alternative hypothesis then is either that there is an association between the two variables. So there is some kind of association or a relationship between the two variables, or I could word that as they are not independent. So I would not say that they are dependent. I would just go ahead and say that they are not independent. After that, we're going to have to go ahead and be able to find our expecteds. And so let's take a look at how we're going to do that. So we find our expecteds based off of our null hypothesis. And so if our null hypothesis is that the two variables are independent, then again, referring back to that, the probability of A given event B is equal to the probability of A by itself would mean that they're independent. So in this particular example, for instance, our probability of coronary heart disease is equal to 190 of them. There were 190 in total that had coronary heart disease over 8,474, which is our total people that was looked at and that were observed. So we get a 0.02242. So if we're basing this off of our null hypothesis, then that would mean that the probability of having coronary heart disease, given that they have low anger, is the same as the probability of having coronary heart disease if they are independent, which would be 0.02242. Okay, so that's how we would go ahead and we would find our expecteds. So for instance, in the low anger people, there were 3,110 that were low anger people. So what we're looking for is what 2.242% of them are. We would expect this probability of people with low anger to have coronary heart disease. Okay, so I have my 3,110 times 0.02242, which gives me 69.73. So that's what I would expect to see of the low anger people with coronary heart disease. Okay, we can put this into formula again. We can find our expecteds by taking our row total and multiplying that by the column total. So our row total, 190, times our column total, 3,110, and divide that by the table total. So row total times column total over table total. So we'd have our 3,110 times 190 over 8,474, which gives me, that 69.73. So that's how we can find our expecteds for that. So if we go through all of these, you can go through and try all of them on your own, or try a few more of them on your own. If you are going to do that, go ahead and pause it for a second, because I'm going to bring the solutions up. So there are your solutions for if you went ahead and multiplied all of these out, right? We have our probability of them having heart disease is that 0.02242, regardless of their anger level, right? And we go ahead and we apply that to each one. Okay, they get our no coronary heart disease expecteds by taking 1 minus 0.02242, and that gives us the 0.97758 probability that they're using here for the no coronary heart disease. So that's how we'd go ahead and we'd find our expecteds to be able to do our chi-square calculations, because again, it's going to be the same, that observed minus your expected. Like all significance tests, in the plan part, you would need to state what it is that you're going to do, chi-square test for independence, and then you will need to state your conditions, and our conditions are the same, that it needs to be random, and we need to state how we know that it's random, 10% if we're sampling without replacement, and our large counts. Remember, for our chi-square, our large counts are that our expecteds need to be at least 5. And as with previous chi-square, as with the chi-square for homogeneity, our degrees of freedom are going to be equal to our number of rows minus 1 times the number of columns minus 1. And that's how we would get our degrees of freedom. And our p-value is going to be the area to the right of the chi-square statistic under our curve, right? Remember, our curve is kind of skewed, okay? And our p-value is going to be the probability to the right of that chi-square statistic that we find. Okay, so as we go all the way through this example of a chi-square test for independence, you will need to identify which chi-square test you're doing. Are you doing goodness of fit? Are you doing homogeneity? Or are you doing independence? So our question here is that does the data provide convincing evidence of an association between anger level and heart disease? So we want to perform a test of, and we would go ahead and we would state our null and alternative hypothesis. Okay, the null hypothesis is, again, that there's going to be no association. You could also word that as they are independent of one another. Where our alternative is pretty generic. It just states that there is an association. But you'll notice we went through all the context. Anger level and heart disease status in the population of people with normal blood pressure, because that was a specific condition of these people. The people had to have no previous heart trouble before, or high blood pressure, or anything along those lines. No significance level was stated, and so we're using alpha equals 0.05. We are still forgetting sometimes to state this alpha. And if this is a 1 point, if we're doing one of these problems on a test or a quiz and it becomes a 4-point problem, 1 point for the state, 1 for the plan, 1 for the do, and 1 for the conclude, you miss that entire point when you are not putting the alpha. So make sure that on a significance test, for any kind of interval, that you're not writing a hypothesis. For a significance test, though, any kind of significance test, you have to write your alternative and null hypothesis and your alpha. So from the state, we move on to the plan portion. So our plan portion is that we're going to state what kind of test we're doing. We're doing a chi-square test for independence. This was one single sample from one population, and we divided that sample up into whether they had coronary heart disease or not, and what their anger level was. So we took the one sample and divided it into two categorical pieces of information. And that will be helpful. That is one of the ways that you can help figure out whether you're doing a test for independence or a test for homogeneity, is where did the data come from? Did you have two samples or did you have one sample? And if you had two samples, then you're looking more at homogeneity, where if you had one sample, you're looking for independence. So we have to state our conditions. We had a random sample. Okay, we were sampling without replacement. This was not an experiment that had volunteers. So we're sampling without replacement, but we can't assume that there are more than 84,740 people that have normal blood pressure. And our large counts, when we did our expecteds, all of our expecteds were at least 5. The smallest one was 14.9. So the condition was met. Remember, you need to list those expecteds. I'm assuming because they did this, that is the same as having listed them all, by saying that it shows enough that you calculated them. But I would be on the safe side, and I would make sure that those expecteds were visible somewhere. From there, we're going to move on to our do. Right? So remember, when we're doing our calculations, we're assuming that the null hypothesis is true. We always need to show our test statistic. Remember, you need to ideally show some kind of work. You don't need to show it for everything. Show the first couple, do your ... show the last one, move on. Here's my test statistic. You can still let your calculator figure it out. You know, your calculator will spit it out for you, okay? But I would still go ahead and show it. Also, remember, you need to state the p-value and you need to state the degrees of freedom. So those are the things that you must show in this do category. Okay, you need the actual test statistic, the actual chi-square value, the p-value, and the degrees of freedom. Remember the p-value, so if I drew this in a picture, okay, so if I, just kind of a reminder of what that p-value really means, right? I have my curve. My test statistic is, gosh, it's going to be way over there. Let's get this curve a little bit better. Okay, so I have my curve. My test statistic is 16.077, right? This is a curve with degrees of freedom of 2, right? We found our degrees of freedom by subtracting 1 from the rows, 1 from the columns, 2 rows, coronary heart disease or not, 3 columns, anger, low, moderate, or high. 2 minus 1 is 1, 3 minus 1 is 2, so we get our degrees of freedom of 2. This is a chi-square distribution with degrees of freedom of 2. And my chi-square statistic is 16.01. So this probability here to the right is 0.00032. So basically there is a really, really low probability that you are going to get that, those observed values that you saw, or higher than those observed values that you saw. There is a really low probability, again, that you will get those observed. Not that you're going to get the test statistic, not that you're going to get a chi-square value of 16.017, but that you're going to get those observed values that you saw in the sample. There's a really low probability that you're going to see these particular numbers here. And our last step here would be our conclusion. Right? Because the p-value, so our conclusion starts the same as it always has. Because the p-value of 0.00032 is less than our alpha 0.05, we reject the null hypothesis. We have convincing evidence, and this is where you put in your context and you explain what that null hypothesis was. We have convincing evidence of an association. So this makes it a little bit different here, of an association between anger level and heart disease status in the population of people with normal blood pressure. Okay, so now that we have all 3 of these types of chi-square test, let's kind of take just a quick reminder of when we use each one. So our chi-square goodness of fit, that's going to be, I've got 1 variable and I have 1 population, right? Holy cow, that writing could not be any worse. Okay, let's try it again. So 1 variable, 1 population. Color is my variable, my population is my box of Fruit Loops. 1 variable, 1 population. Okay, your chi-square for homogeneity, like we mentioned before, this is going to come from 2 or more samples. So I'm going to have 2 or more independent samples or groups here. Okay, and then for my chi-square for independence, this one I'm going to have 1 sample, and I take that 1 sample and I split it into, I divide them into 2 different categorical groups of data. Okay, so looking at this example here, we're going to read it, go through it, kind of think about which kind this would be, which chi-square would I use for this. Okay, so take a second and read it and look at the mini-tab data. Okay, so now that let's look at the mini-tab data, make sure that you can pull data out if they give you printouts of something like this. Pay attention to, usually down at the bottom, they give you totals. Okay, so just like at your tables, you've got totals at the bottom and on the sides. You have your chi-square value, you have your degrees of freedom, and you have your p-value down here at the bottom. Okay, if you needed, you've got expecteds within. Okay, this is basically your key is along the top. So for instance, I've got males and females on the top. And so just like over here in my table, and then here where it says 1, and then it says 2, this is my yes and no's. So this would be yes, and this would be no. Okay, and then you can see how these match up, right? How they match up with our table. How we've got our 7 and our 29, right? Our 31 and our 50. And then we have these right below it. This 11.69, 24.31, 26.31, and 54.69. Those are your expecteds. Okay, so I just need you to be able to read that kind of data if they give that to you, because they could give you the data like that, and you just need to interpret it. So our first part A of the problem here asks you to explain why a chi-square test for independence and not a chi-square test for homogeneity should be used in this setting. If you think back to what we said before, where did the data come from? Well, the data came from one random sample of 117 college students. So it came from one random sample of students, and then that one sample was broken into two categorical variables, gender and then fright symptoms. So your official answer here, the data were produced using a single random sample of college students who were then classified by gender and whether or not they had lingering fright symptoms. Your chi-square test for homogeneity requires independent random samples from each population. So it would have required a sample of females and a separate sample of males, or a sample of yeses and a samples of nos, but from each population. So part B asked to state an appropriate pair of hypotheses for researchers to test in this setting. So we're using a chi-square test for independence. Okay, and so our null hypothesis should be that there is no association between gender and ongoing fright symptoms, or you could say that that gender and ongoing fright symptoms are independent of one another. Your alternative hypothesis would be that there is an association between gender and ongoing fright symptoms, or that gender and ongoing fright symptoms are not independent of one another. You could word it either way, just stay consistent. If you are talking about there being an association versus no association, then keep going with that route. If you choose to go independence, then keep going with that, but don't change it. Don't say that there is no association between gender and ongoing fright symptoms, and then your alternative says that they are not independent of one another. Be consistent. So part C wants to know which cells are contributing the most to the chi-square statistic and in what ways these cells differ from what the null hypothesis suggests. So if we look here, we've got the men who admit to having lingering fright symptoms account for the largest component of our chi-square statistic. So as we're looking at it, these are in the mini-tab data, right? We have our observed. The first number there is the observed. Then we have the expected, and then this is the portion of the chi-square statistic. If you add all of these bottom numbers up, you get this chi-square statistic of 4.028. So our biggest number there that's adding to this statistic is the males who admit to having lingering fright symptoms. Far fewer men in the sample admit to the fright symptoms than we expect to see. So in part D, when we're interpreting the p-value here, so if gender and ongoing, so there's our curve, right? And so our test statistic is at 4.028. Oh, that's not right. So here's our p-value, right to the right of it, 0.045. And so if gender and ongoing fright symptoms really are independent, because remember, we assume our null hypothesis is true. When we're interpreting a p-value, we assume that the null hypothesis is true. So if gender and ongoing, assuming the null hypothesis is true, if gender and ongoing fright symptoms really are independent in the population of interest, there is a 0.045 chance or probability of obtaining a sample of 117 students that gives us that chi-square statistic or higher, because it is greater than, and so the second part of this question asks what we would do at an alpha of 0.01. So because 0.045, our p-value of 0.045, so this is our conclusion. This first sentence here is our interpretation of the p-value. The second part here that starts with the because, that's our conclusion. We would fail to reject the null hypothesis. We do not have convincing evidence that there's an association between gender and fright symptoms in the population of college students. So the very last bit of this chapter is about kind of what-if questions. So what if you wanted to compare two proportions? So if you wanted to compare two proportions, go ahead and just use a two-sample z-test. You wouldn't necessarily use a chi-square. You would go ahead and just use a two-sample z-test. Okay, so if you were comparing like the difference between proportion 1 and proportion 2, okay, like we've already done, right? If we had a null hypothesis that looked like this versus an alternative hypothesis where the two proportions do, the difference between the two does not equal 0, then we would just go ahead and use our 2 sample z-test that we already know how to do. Okay, another one was if you have quantitative data, you can group that into categorical. Like for instance, let's say you were looking at income somewhere. The example here is about income. So if I'm looking at income, that is quantitative data. I make this much money per year. But I could take that quantitative data and I could turn it into a category. Like for instance, I make under 10,000 a year. I make between 10,000 and 19,999. So now it becomes categorical data instead of quantitative data. And then I could do one of my chi-square tests on it. Okay, and then the last kind of what if is what if my expecteds, like for instance here, my expecteds are not 5 because they have to be 5. And so if my expecteds are not 5, I could consider combining, for instance, group quarters along with other quarters. If I combine these, then I do get expecteds of at least 5, and I just combine these 2 categories together into group quarters and other. And so again, make sure when you're reading this data, if you look across the top, you see your 19, 20, 21, 22. Okay, that's our age groups that we had up here. Okay, and then the 1, 2, 3s, and 4s, that would be living parents' home. Let's get rid of that. Parents' home, another person's home, your own place, and then 4 would be the group other combined. Okay, and I get my observed, right, is my top one. So my observed numbers, my expected numbers, and then the portion of the chi-square statistic is the bottom one. All right, so observe, expected, its portion of the chi-square statistic. And I see that for each one of them. Okay, and then down at the bottom, I have my summary information. My total chi-square statistic, my degrees of freedom, right? 4 minus 1, rows minus columns, rows minus 1 times columns minus 1, which would give me that 9. 3 times 3 is 9. And then a p-value of basically 0. Okay, so that's, again, look at that mini tab data so that you can interpret that on your own if that is given to you. And we are all done with chapter 11.